Right. Can we start? Today also, for a reason I came early because I want to squeeze in a few more questions on EC if possible. And there are specific things that I thought of discussing. So that's why I came a bit early. Let the others join in. Let us start with that. So if you remember on last this class, we had discussed a very important part of AES transformation. And first of all, there were four transformations that we came across. There was sub bytes, there was shift rows, then there was a mix column or mixing operation. And finally, there was something called as add round key. So these were the four operations for every round which we are supposed to undergo, except for that for the last round where the mixing will not be happening. And in that aspect, we observed that for the sub bytes, if we recap a little bit, for sub bytes, it was basically a table with respect to which we were trying to permute the data or the table and or a 4x4 state matrix for that matter. And after going through that, we went through something called as shift rows, where the four rows will undergo a specific set of operation, where the zeroth row will not have any change. The first row will have the first byte will be left shifted. Then we have second row where the second byte will be left shifted. Two bytes will be left shifted. And the third row case, the three bits will be left shifted. So that was the shifting operation, which was relatively simple in fact. Then we found out that there is a way of doing it, something called as mixing. And in mixing, what happens that there will be a template of a matrix which will be provided to us, which is a standard matrix. In fact, that matrix also was very easy to understand because it was only a combination of 2, 3 and 1. And if you remember, the first column was 2, 1, 1, 3. Then there was a shift of right shift or left shift. If you say it was 3, 2, 1, 1. Then it was again 1, 3, 2, 1. And then 1, 1, 2, 1. So it was very easy actually. And based on, we haven't discussed the process of doing that multiplication of that template matrix to that of each column of the state matrix. So that part we are going to discuss today, in fact, because that requires a separate set of understanding. And but keeping that aside, but after doing that, the mixing part, we will undergo something called as add round key. But for add round key, post the zeroth round, that's the first round onward, we will require the keys to be generated by some algorithm which is called as key expansion algorithm, which is mentioned over here. And if you observe, if you remember, we had discussed this specific example in which we have found out that initially we will need the W0, W3 up to W3, which we will generate from the key itself. But post that, we will try to use an algorithm in which there will be two separate elements, which is rot word and sub word, which will be added on top of with something called as a rotational constant matrix, which will look something like this. And depending on which round we are in, we will XOR the process of the finding of the subword to that of the rot constant. And finally, we will achieve a temporary word, which will be mentioned something like this. And also I told you this temporary calculation will only be relevant for the left hand side bit. That means W4, W8, W12, 16 onward. Because the rest of the elements, rest of the words will be depending on previous words. So we don't need to calculate temporary bit, temporary word for any of the other cases. Only for the leftmost side bit, we will require the leftmost side word, we will require this T calculation. So in this case, particularly when we are trying to find out T1, that T1 will be XORed with W0, which is again already given to us. And we will finally get what is called as W4. And eventually what will happen that W4 along with the help of W1, we will try to find out what is W5 and then that W5 will be used for the next set of calculations and it will go on. So basically this transformation and the key expansion strategy is what we have discussed, unlike to the one part that we are left with, which is the mixing of the mixing process, how it does. The problem is it's not that difficult to understand because we have a 4x4 matrix or the state matrix. And that will be multiplied by some kind of a template matrix. But the multiplication will be a polynomial multiplication, not the generic matrix multiplication. So that's where we start our discussion with. So this, before going to this document, hopefully this is visible to all of you. Before going to this document, two things that I should tell you. First of all, this document is already there in ZTop. Along with that, I will find that I might skip one or two numericals over here due to lack of time. but this document will have at least 4 or 5 numericals which are made by me. Okay, so it doesn't have any other solution apart from this what is given over here. All right, but those are the template or those are the type of numericals you can expect in your CAT 2 from this particular segment. So that's why it is very important. This document has a heading called AES mixing procedures and numericals. Like that, it might be the heading of the PDF. That's one thing. Second thing is, for all these cases, like I told you on last day's class itself, I have prepared one document of tables, okay, which are relevant for your usage, because I was suggested that since you are all like it is what the expectation is that you will all carry a textbook with you. So the textbook will have those tables in that, and you will search that during the exam and you will do it accordingly. But I thought that since in that books, first of all, finding it out will take some time. Secondly, there are n number of tables which are there, which might not be relevant at all. But unfortunately, you will look into that and you will make a mistake. So what I did, I made a 6-page document in which both sides, like 3-page document actually. So in that, I have included all the relevant table which are required for you. Only the relevant table. And I've made my signatures and everything, and then asked the CAT coordinator as well as HOD sir. So that document you take a printout and keep it with you during the exam. It will be allowed. Alright? But don't write anything on the paper because that will be considered as malpractice and all those stuff. So please bring that table and that will be enough. Even if you are not carrying the book. Okay, that's what I'm telling you. If you are carrying a book, mostly you will be getting it, but again, finding the page number, right table, it might be a problem for that matter. Okay? So these are the two things. So without wasting much time, let's discuss this part of the mixing process, how it goes. Remember, we are doing post the shift operation has taken place. Just visualize intuitively that you have the block. First it goes to subwise, then it goes to shift rows, then it comes to this part. So this element that you are looking at, this S matrix that you are looking at over here, this S matrix that you are looking at over here is the outcome of the shift rows. Just imagine. Alright. Now, if you observe again, this matrix is what we have discussed right now. This is the template matrix given by T. That's already discussed in PPT. Now the point is, for this purpose, we will require a multiplication. So how the multiplication will take place? Please see this combination. That's very important. We will take the first row of the template matrix and we'll take the first column of the source matrix or the state matrix. Yeah. Alright, and we will multiply. This combination will undergo how that this row of the first row will be multiplied with the first column, and the resultant output will be the first corner element of the resultant matrix, which might be called as R1, R2, R3, R4, so on and so forth, to R15 most probably. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Alright, so this R, that reference, I'm just giving it as a name. That will be the outcome of this whole process. So after this multiplication and the respective XORing operation, which I'll tell you, the first element R1 will be the product of this first row and the first column. Same way, keeping the first row intact, if you take the second column, that will be the entry over here in R2. Alright? Same way, keeping the first row intact, if you take the third row, it will be R3 and R4, and it will go on repeating itself. So in this particular example, we are trying to find out R1 and R2, just to make you feel understanding on the process. Okay? So let's do one by one what exactly we are supposed to do. If you observe, now let me just write it down first. I'll go back to the other things which you mentioned. So if you observe that this is what we are trying to do. Observe very carefully and pay attention to this. So you can observe that we are multiplying it. Just to make you understand, I have made this bracket and in which 2 is getting multiplied to 36. Why? Because if you observe here, 2 is getting multiplied to 36. 3 is supposed to get multiplied by A3. 1 to 7C and 1 to 0B. And in between, like in case of matrix, we have addition. Here we will have XOR. So that's what we are trying to do. Right? Understood this one? So basically each and every component should be considered. It will be multiplied and there will be an individual zoring between the found out element. Now the zoring part is not that difficult. We'll see that. Problem is with this multiplication part. Because these are all polynomial representation or polynomial multiplication that you have to do. Now to understand that, let me just give you a small example to understand, make you understand. That's easy things to understand to make this thing. First of all, this is the polynomial expression that you are looking at over here. Okay, this happens to be the representation, polynomial representation for a field of 2 to the power 8. Why we are considering 8? Because we are considering that 8 bit at a time we are doing it, because 1 byte we are considering in that way. So you have the total. If I represent those 8 bytes or 8 bits in a polynomial expression, this is the expression it has. Okay, this is the expression. You can see 1 plus x square plus x cube, like up to x to the power 7. So the maximum power of x is 7 and the minimum is 0. Meaning that don't need to panic. Nothing we are going to do much over this. Only the representation is where the polynomial thing will require. So now, keeping this in mind, let us try to take the first of the example, 02 multiplied by 36. The first option is you have to convert this to binary values. If you observe closely, I have done that. I have made sure that both are binary values and see the representation of this polynomial expression. 1 plus x square. This is the fundamental, the standard template of the polynomial expression. And if you observe carefully, the values that is defined by 0 and 2 has been mapped over here. So what will be my expression? My expression for the 02 will be nothing but x, because only in x we exist a 1. Should I repeat once again? If you closely observe for 0 and 2, we have divided that into space in binary form. Now you gradually have one exist template for you. You are just arranging the data 0, 1, 0, 0, 0, 0, 0, 0. Now all are 0 except for this x equal to 1. So the final polynomial expression for 02 is x. Okay? Next one, if you consider the 36 over there, 3 is given by this and 6 is given by this, and in the same manner, template which is given, we have arranged it. Okay, so intuitively you can say this is my x, this is my x square, because ones are present over there. Then x is 4 is there, x is 5 is there. So you can see that the final expression for this is x to the power 5 plus x square plus 1. Any doubt over here how we are planning it? And so now 2 is represented by x and 36 is represented by x to the power 5 plus 4 plus whatever it is. Now you multiply. These two polynomial expressions, x polynomial expression is to be multiplied. You can see here. Correct? And the final expression that we are getting after this multiplication is x to the power 6 plus 5 plus 3 plus 2. Not 2 square I'm talking about. Now the trick is, after that you are received, you have to get back the binary data. How will you get the binary data? Whichever power is missing, those are 0. Because the coefficient was 0. That's why the power is missing for x. The power is missing for maybe x7. Right? Because x, that's a template for us. So maybe what we can write here is, we could have written an x7, but it is missing. We could have written an x4, which is missing. We could have written x, and we could have written x to the power 0 also, which is missing. So all those missing elements will be considered as 0. And wherever the x values are present, those will be considered as 1. And the data that you are receiving over here is the product of the multiplication of 02 into 36. Am I clear with this? Because this will go on for all the cases, except for an exception, which I'll tell you. But is there any problem here? Okay? So this is the part of 02 into 36. What is the next one we have? The next one that the multiplication we have is 3 multiplied by A3. Same pattern, same thing will happen. So 0 should be 03 should be represented in binary form. A3 should be represented in binary form. So let's go back. So I have reduced the step here. So the final expression is coming as x plus 1 for 03, and for A3 it is coming as x to the power 7 plus 5 plus x plus 1. This is same as that of the previous one. The problem comes in that there is a catch over here. And the catch is, if you do multiply both these two factors, you are getting an expression like this, and unfortunately, we have a power over here which is x to the power 8. Right? But we have already concluded that the power can only be maximum up to x to the power 7. It can't be x to the power 8. So we have to do some kind of a round off. Just like we have done for modular arithmetic, the same thing will happen over here. Except here this round off will be done by something called as irreducible polynomial, which I am omitting the whole discussion all throughout, because it's not needed for you, except for one thing that you need to know, and that is, whenever you will get certain element, please make a note of this, x to the power 8 should be replaced. X to the power 8 should be replaced by the expression x to the power 4 plus x cube plus x plus 1. Wherever this is actually coming from, you can see it's mentioned there are 30 odd other combination that is possible. But when the irreducible polynomial of to the power 8 was conceived, out of the 30, this was the first of the solution which was provided. That's why this is considered as the standard for x to the power 8. So if you are getting x to the power 8 as a power, reduce that using this value of x to the power 4 plus q plus x plus 1. Please underline that or keep a note of it. That's the only catch over here. Rest of the things are same. So if you do know that, now you replace this x to the power 8 by x to the power 4 plus 3 plus x plus 1. And if you observe over here what I did, now no 8, nothing is present in this expression. Naturally, because we have replaced it. And wherever you find any common terms, exclude that. For example, you can observe over here x and x is present. So x and x is getting discarded over here. This x remains because there is nothing to discard that, because there is no such like even values are not there. But if it is there, I think in the previous example, I think there will be some, if I'm not wrong. No, it's not there. In the previous example also not there. But anyway, whenever you will get the common power, like suppose x square is also there and also another x square is there, you discard that. Okay. So whatever is remaining is what I have written over here. X to the power 7, 6, 5, 4, 3, 2, 1. Please arrange them properly, because based on your arrangement, your ones and zeros will be assigned to them. Understood? So based on that, we have arranged and we found out something like this. Any doubt over here?
Sure. Only x square and x square, 2x squares are there. Just discard them.
Yes.
X square.
No. If x square, like you have an x square and also another x square is there, you discard them. Simple. But suppose you have another, like in case here, there are 3 x's, you can see. So 2 gets cancelled, the other one remain as it is. That's how it is. It's like if it is even, you cut them. If it is odd, you keep them. Just like normal, right? Done? So the first expression 02 into 36 has given us some binary value. The next second component has given me some value. Likewise, the third and the fourth will also give us some value. They are advantageous because we are multiplying by 1. So if you see here, we are just multiplying 1 into 7c and 1 into 0b. Which is simple because we are multiplying with 1 and eventually it will come as like the data itself. So your 7c is reflected directly and your 0b is reflected directly. So now we have 4 sub-components to the multiplication of the first row to that of the first column. And that is being summarized over here. You have the 4 such components which I have written it down. Am I clear with the finding of this 4 element? Should I repeat anywhere? Any step? We are just trying to do a polynomial multiplication, but for that we have to arrange the binary data in the way I told you. And if at all an exception comes in of x to the power 8, you have to replace that by the irreducible polynomial of x to the power 4, 3, x and 1. Like that. Based on that you get that, And as per our rule, if I go back to the first slide itself, as per the rule, where is it? Yeah. We have to XOR all the products. So this I have got one, this I got some binary value, this also binary value, this also binary value. Now you have to XOR them. So that step is being shown over here. So these are what I'm XORing. In that also the rule is very simple. If there are even number of ones, it will be 0. And if there are odd number of ones, it will be 1. So you can see very clearly column wise column you go. Like here in the first column, if you see odd 1, so 1. There are even number of ones, so 0, so on and so forth. And finally, whatever you are obtaining over here, as you can see here in the arrow, this is my R1 value. So only to find one element of the resultant matrix, you have to perform 4 such matrix multiplication or polynomial multiplication. That's where things becomes a little tough if you don't know the process of how to complete. And unfortunately, most of the textbooks, you will find that this process is not mentioned anywhere. So you will be like given the final expression that this is what is happening post the mixing thing has happened. And you will like completely get puzzled that why on earth this is looking like this. Okay. So the matrix multiplication happens, but it happens in terms of the polynomial matrix multiplication, not the generic expression. So in that way, you can also find out what is my R2. I've given over here in the PDF itself that what is my R2. Okay. So that's how we are doing it. So my row 2, the row 2 of T, that means the template matrix. The second row we will consider and we will take the first column of the element, and that if I multiply, that will be my R2. Similarly, R3 and R4. So R5 again will be the first row, second column. R5, like that. Okay? And R5, R6, R7, that's how it repeats. Am I confident with this? So suppose you are given a matrix and you are asked to find the mixing phase solution. Given the fact that you know the template of that, of the matrix, will you be able to solve it easily? Let me give you another example maybe just to show you at least. So suppose, this is the question, suppose, some example I thought of sharing you. So suppose for example, this is at the 6th level, we have an output or a state matrix given as this, 72, 80, something like this. Now the question is find the final output matrix or state after the round ends. Okay, given the round key at this point is this. That means the expansion box has worked. Okay, the question is not to find the key. The round key is already there. Now you have a state matrix. It should go through how many slides it should go through? How many states it should go through? What is this element, this matrix, where exactly it lies if you visualize the block diagrams? This is post the pre-round. So it has to undergo sub-bytes, it has to undergo shifting, it has to undergo mixing. And after that you have to do the add key, add round key, and then only you will get the final answer. Alright, so this is one of the example I thought of sharing with you, just a brief understanding of it, just a brief understanding. So you can see over here, I have done that. I'm skipping for the timing because of lack of time. Maybe you can just look into it. So this is another example of finding out the keys or the multiplying process. Again, it's given over here. Same thing, same process will be followed. So kindly look into it. And if you have any doubt, you can just let me know. Because it's already been uploaded in your VTOP. So I hope that within this weekend, you can at least look into it. And if you have any doubt, you can come on Monday and let me clarify. So this is how it works, and you can see the final stage, the round key. This is also nothing but because the round key is already given to us, we can just XOR. How round key was working? Add round key. Add round key. Suppose you know the add round key. What was the process? How do I get the final stage? See, you have forgotten again. Column, take the first column, XOR it with the first column. Simple as that. That's why I'm keeping on repeating the process. Because if you don't repeat process, if you don't remember the process, you won't be able to solve. Just by looking at the solution, you won't be coming up with anything. So please try to use any matrix and try to apply the process and get the answer. It will not happen during the exam, I'm telling you. Just on the day of the exam or before the exam, sir, I'll go through the material and it will be fine. We will carry anyway the material and it will be done. No, it won't happen. Please practice them. All right. So this is one of these. So this all column wise XOR operation is happening, and finally we are getting one of these elements over here. Just like that. Okay. This is one of the type. Very similar kind of question might come. Suppose you are given a state matrix. You are asked to find out what will be the outcome after the shifting operation took place. So you have to remember that sub-byte also must have happened. So sub-bytes, then shifting, then the output will come. Suppose you are given a state matrix, you find a 4 cross 4, I'll just do the shifting and it will be the answer. No, it doesn't happen. That's it. Yeah. So please take care of that. The last problem before we end up, I think in this you will find a lot of solution in the question, very similar, which I think I can omit for the time being. You can look into it later. Let me show you another question, which I think in fact, initially I thought that I'll not share this question. I'll just give you directly during the exam. But then I thought, no, this will be too harsh on you. You might have an issue with that understanding. So the question is something like this. All right. So the plain text is provided to you. And the key is also given to you. All right. Now, in that case, yeah, so the plain text and the key is provided, but what is not provided is the matrix. Because up to this point, what we have done using a matrix. It was a 4 cross 4 matrix, the data, some hexadecimal value is given, and then we are processing it, right? But here there is nothing given, but proper characters are given. And also you can say, these are some character, this is also some character, this is space, we are providing that, it's mentioned it somewhere down the line. So to answer this question, you will need the ASCII table. This is also provided in the table that I was telling you, in the sheet. So in that, what is happening, that basically in over here, for each of this letter, there will be corresponding hexadecimal value. So basically, the table or the 4 cross 4 matrix has not been provided. You have to create it. Am I okay with this? This part? Nothing else. It's just that we have to convert that back. I thought, as I said, I thought of giving it to you during the exam itself, and I'll ask you to solve it, and you won't be able to solve it. And sir, we have not done the question properly. Like that, many comments will come. So I thought of just giving you one of these examples, so that at least some other example you can do it on your own. Kya hua? Yeah. That table itself is having that. You will find it. Okay. So what happens is, now the question, now let's go back to the question. Let's see whether that you identify. Suppose the plain text is provided and the key is also provided. Oh, one thing for sure. I should not be telling you this, but still I'll let you know. The keys you can observe over there are multiple S's given. All right, at the end. Okay, that's not because that it's to indicate that even if in your deep sleep, in your sleep and super sleep state, that this comment is not, the plain text is not correct. But no, it's not for that. The two S's have been added to make it as a 16-byte information. So the rule is, if you are given a smaller key and you have to make that 16-byte of information, add the last byte continuously. Like here I have done dreams and SS. The last two is just added to make it 16-byte. It's unlike to the previous cryptographic techniques where we had added X or Z, the redundant values which we have not used enough. No. The last bit you just add up. Okay, that's one of the observations. Now the question is, show the output after pre-round transformation. Can anyone tell me what we are supposed to do over here? Suppose you have deciphered the table and use the table and you found out the hexadecimal value. What we are supposed to do after this? Which process we are supposed to do? Huh? Do I have W0, W1, W2, W3? Do we have that? Can we create that by any chance? How we can create that? Because this is my key, this is my basic structure, this is my starting of it. So we can easily do one thing, that the plain text matrix and the key matrix, we can arrange it accordingly. And as we know that for each column that will be considered as W0, and W1, W2, W3. So basically the words are to be found out from the matrix. See? If it is, we have done this, next what? Do I need to show any table? Do I need to refer any table or permutation, anything? No. What we have to do then? Basic XORing, column to column. So that's what is being done over here in this particular question to get the solution. Okay. Similar questions. And now, yes. I'll go up. Where? Here. Yeah. This I mentioned over here. Spacebar in keyboard is expressed as SP in table. In table, you will find it is mentioned as SP. So that has a 20 value. So that's why the 20 has come. Okay? It will be mentioned. If it is like this, I'll mention it in the question itself. And now you can see this last one before I end up this AES, because it's creating a kind of nauseatic feeling for me with AES. So this question is a continuation to the previous question. Alright, this is a continuation to the previous. Suppose you got that answer. Now you have to show me the sub-bytes, shift rows and mixing only for the first entry of the column of the state matrix. Only one of the entry. It can be one entry, or I can say show me the first column entry for the mixing element. Because 16 element multiplication for a CAT period, it's impossible. In that case, I have to give one question for 50 marks. Can't be possible. So you only might be getting like third row, all the element, or third column, all the elements you mentioned. Or the first column, all the elements you mentioned. Okay? So that's how it turns out to be for AES, the questions on how it can be. So please go through this material, check the documents, how it is being done, take the resources and try to solve it on your own. Okay? Check the timing, how much time it takes to solve this kind of question. Because based on that, you will arrange for the others. Because remember, for CAT 2, the syllabus starts from Chinese remainder theorem. Remember, that's where we started off in the second module, last part. From there, we have done this part. So that's the end of almost the third module. And by the time we have the two classes, I'll also touch on something from the fourth module also. There's a reason for it. I'll tell you that on Monday. All right. So let's go back to our PPT and just go through some of these very simple things, I would say, compared to what we have discussed so far, because it's primarily a theory structure of it. But this is required for us when we discuss about RSA, which happens to be the algorithm for a symmetric cipher. Alright. So this is the structure for pseudo-random number. How we generate a pseudo-random number. Because here the pseudo-random number primarily is important because we are generating keys. So this principle, तुझे कब जाना है? अभी निकल जाना? The pseudo number generation is very important because we are generating the keys which are supposed to be random in nature. Alright. So for that, usually there are two ways of doing it. One is called as counter mode, which is this one. And the other one is called an output feedback mode. In counter mode, what happens? You just understand this very briefly because it's not of any use as of now. Counter mode is, if you observe the diagram, there are some counters given. Counter 0, counter 1, like that it's given. So what will happen in the transmitter? There will be a block which will look maybe some block maybe. And in that block, what will happen? There will be a seed value. Initial value will be provided. Based on the initial value and the timing, okay, our algorithm will make sure that there is some random data that will be generated. You can see over here the block cipher encryption is happening, and you can see this arrow. So the seed value and the counter will generate some random value which will undergo an algorithm under this block cipher encryption, and this is nothing but the key. That's the random key will be generated. Based on that, the plain text will work on it, and finally the cipher text will be generated. But if you observe C1, C2 up to Cn, ideally this is the block diagram for a stream cipher technique. It will be applicable to block also, but mostly what happens is that we are generating, suppose K1, K2, K3, like that. In DES or even for AES, we have generated random keys, right? So the same thing, initial part is purely random, and that is done by this kind of a technique. So in the transmitter, you will have these counters. The same counters will be synced to the receiver. They will be synchronized to each other. So whatever you have done with the generation part, the reverse will be done at the receiver. But ideally, it is very difficult because the synchronization to keep it for both the transmitter and the receiver is not always correct. So there will be some error. For that matter, the second easiest way of doing it is the output feedback, where you can observe that initially there will be a vector, initial seed value will be given. Seed value is nothing but a starting value. You will see, so I will show you one example after this. So there will be initial value. Based on that, you will generate an output. That output will trigger the input to the next one. It's very similar to the key generation algorithm that we had discussed a few moments back. Okay, so that's how the random bits are generated. And as here, there is no counter or any timers for that matter. So there is no chance or no need of any synchronization that needs to be made between the transmitter and the receiver. So this is a more preferred solution compared to the first one. Okay, although both are used in different applications. So let me just directly go to the stream cipher, where we will end our discussion a bit, because block cipher is what we have discussed so far. 64-bit data block, 128-bit data block. So block cipher is what we have discussed. Please don't talk. Okay, focus on this. Stream cipher is where we are actually taking each bit at a time, and we are trying to make sure there is an encryption that is happening with respect to each member of a key, and we are generating a random data. So just to understand that, let me show you this diagram. So you have this Ki, which is generating 1 bit of key, and we have a Pi, which is generating 1 bit of plain text. Maybe there's a long plain text, but 1 bit at a time is being processed, and we are getting an encrypted output which goes through the secure channel. And hopefully, even if the intruder comes in, it is so much secure that the data is perceived at the decryption level. Now, this idea, the diagram that you are looking at, this is a kind of an utopian diagram or a theoretical diagram which is never possible. The reason being, in this particular example or the setup, it was claimed that if this process is happening, that Ki is generated through a random sequence bit, where here the counter mode or the output feedback mode has been used, and the Ki is generated which is random. This model suggests that there will exist a secure key exchange channel through which this Ki will be shared to the end user over here, and using that same Ki, it will decipher the data. That is what the assumption is, that you have a secure channel. Secure channel means there is no intrusion. That's what is expected. So that's secure. Through that secure channel, you are sending the data to the receiver. And the receiver will also have the same key which you have sent. He will use, and it will be deciphered. The problem here is that if there exists a secure channel, then you could have sent the plain text directly. Why will I need a key itself? Right. So the basic fundamentals to cryptography fails in this case. And that's why this is, although it is a theoretically it is possible, but practically this is an impossible solution. Right. So that's why the thing that comes in on very handy, you can see this later. This one is the process of generating the random bits in a much more secure manner, and that is what we called as the feedback shift register. I think all of you have seen the feedback shift register somewhere in your curriculum. Digital logic. Have you been studying this? Known to you? Achha, I'll just do it in terms of what we need for the time being. What basically happens is you have multiple memory elements or register element, whatever you call them. And based on some function, which you can observe over here, feedback function, we will define some rules. That rules will be shared both at the transmitter and the receiver. Alright? Both the intended party will know the rules. Rules basically, there is the zoning operations and all those stuff. So that will be known. There will not be any sharing of keys as such. Alright? Now, the feedback shift register works in the principle that that functionality should be implemented in a box of this nature. And how it works, let's see. Suppose we have this function B4 XOR B2 plus XOR B0. That means we have, and the output is called as B5. So if this, we need to develop a shift feedback register setup, it will look something like this. See for yourself, it's self-explanatory, it's very easy. We have B0, B1, B2, B3, B4 because these are the input data, and B5 is over here. So the function that you are looking at, the feedback function that you are looking at, is actually operating with respect to only these 3 bits. Now you have a drop down table. Suppose you have an initial feed value for B0, for B1, for B2, B3 and B4. Based on that, you actually can predict what will be B5. And every time, every clock pulse, what will happen? There will be a shifting process that will take place. That means B4 data will come to B3. You can see the arrow over here. B3 will come to B2, B2 will come to B1, B1 will come to B0, and B0 based on the function will reflect it into B5. So that's basically the way we usually generate a random sequence of data for the modern stream cipher technique. Let me just give you one example before we end up our discussion. This is very simple one. You can see this is B1 XOR B0. Suppose I give you this kind of a function and I ask you to generate a feedback process or a diagram of this nature. So you have to do the same process. You can observe here B1 and B0 and B4 is the output. All right. And the number of elements will be known to you. Here it's not mentioned, but suppose here 4 are the total elements which are present. All right. Now the equation wise, the XORing is happening between B1 and B0. And if you look closely to the table, there is an initial seed value which is given. Initial seed value is given. That is apparently present over here. So at the initial condition, 0, 0, 0, 1 is being fed to B3, B2, B1 and B0. Right? But as for the function, B1 and B0 is getting XORed and that output comes to B4. So if you observe, B4 is 1 over here. And the next cycle, B0 comes here, B2 comes here, B1 comes here and B4 has come from this point. And it will repeat once again. Again, B1 and the B0 content will be XORed. Whatever be the output, that will go back to B5. So again, the B5 comes over like this. And it will go on. Here in this question, 20 transitions are to be asked. So you can see the last entry over here is 20. So this element that you are looking at over here at the right side of the corner, this is my Ki. Understood? So the random keys are generated by this process, which has, based on the rounds that you want, the random keys will be generated one after the another. But the point over here is why we require RSA after this, why we are not stopping and why we are not happy with only this configuration is given in this last slide before we end. I know I have extended a bit, I think. No, I have not extended. So if you observe here, what is the problem? That after 20 rounds of process, the data is coming like this. But if you closely look at, although it looks like a random data, but after a certain period, the pattern repeats itself. And that is one of the default property of a feedback shift register, that the maximum period of an LFSR will be 2 to the power m minus 1, where m is given by the number of memory element or the register element. Right? So in this case, what is happening? Although we are generating as if a random sequence of data, but eventually we are getting a repetitive element, and as per the logic of randomness, that's a con or a disadvantage as a property. If you are having a pattern which is repeating multiple times, then means the key is not adequate enough. People can identify that what is the sequence of key is coming, right? So that's not a very good option. So that is where this stream cipher technique will lead to something called as public key cryptography, in which the first time there will be a public key which will be shared with everyone, whoever has it. Even if the intruders have it, no problem at all. But there will be something called as private key as well. And the private key will be specific to the user who is the intended target. So based on that, this RSA works. And why we are doing this is because the previous methods are not foolproof as such. But RSA gives us a very good understanding of this. The public key cryptography takes care of all these problems of the stream cipher technique. So we'll see that in RSA, and you will soon find the RSA as well as the fourth module portion that I'm telling you. They are the most easiest part of your portion for CAT. The algorithm, although looks very ornamental and all, but the process is absolutely simple. Okay, so please don't miss on Monday's class where we'll study the RSA and hopefully we'll solve some numericals on it. Yeah, thanks. I'm 1 minute. Just give me 1 minute.